All right, so we're still dealing with solids of revolution and specifically using either the disk method or the washer method to find their volume. But in this video, I'm just going to go a lot quicker than I did in the last video where I was really more trying to stress the theory and the ideas behind this topic. So for this first example, let's see, we're given a region and I'll sketch you the graph. I don't know if you really need the graph, but it might help. So here are my surprisingly decently drawn graphs of sine of x and cosine of x. And so I guess the first thing we want to do with this problem is identify the region that we're talking about, the bounded region that we're going to end up rotating around the x-axis. So it's bounded by sine of x and cosine of x, so the red and the green curves respectively. And then x equals 0 and x equals pi over 4. So x equals 0, that's this vertical line, also known as your y-axis. And then x equals pi over 4. Well, let's see, pi is right here and pi over 2 is here. I guess pi over 4 would be halfway between 0 and pi over 2. That makes sense because at this x value, the sine of x is supposed to be the same as the cosine of x. And maybe you remember, maybe unlikely, from back when you had a unit circle memorized, but that the sine of pi over 4 and the cosine of pi over 4 are both the square root of 2 over 2. At any rate, the region that's bounded by these guys, let's see, above by green and below by red and on the sides by the blues, appears to be this region right in here. So what we're doing is we're taking that tiny little region and we're going to rotate it around the x-axis here. So if you're really good with 3D, maybe you can kind of imagine what that would look like in some sort of an animation if we revolved this region about the x-axis here, the 3D figure that would result. And if you can do that, that's great, but really you're not even going to need to be able to do that because all we got to do is set up our integral and evaluate this thing. And I don't think that'll be too hard to do. It looks like our x values are going to go from 0 to pi over 4. That was kind of obvious when they gave us these two bounds here. And our variable of integration is going to be dx. I guess because that's the only thing we know how to do so far. But later on, I'll show you how it could be dy and what that would look like in your picture. And then if you think about what you're going to integrate, well, if we take any arbitrary cross-section here, a cross-section of the three-dimensional figure that would result if we revolved this shaded region about the axis, what a cross-section would look like would be a washer. And to figure out the area of that cross-section, to figure out the area of a washer, all we got to do is figure out the area of the outer circle and then subtract out the area of the inner circle here. And the outer circle, again, drawn in green to really emphasize that where it comes from is this curve, y equals cosine of x. You can kind of picture, if you can tie together the radius of this green circle with the distance from your x-axis up to the green curve. That's a really good way to test whether you're able to visualize what a cross-section would really look like. At any rate, the outer radius is going to be the green curve, which is just equal to the cosine of x for any given x value in here. And the inner radius will be the red curve, which is equal to the sine of x for any x value within this interval. So we can represent the area of a given cross-section by taking pi outer radius squared minus pi inner radius squared, and writing that with a few more parentheses than maybe you need to try to emphasize where all the pieces are going. That would give us this expression here. And again, the hardest part is being able to turn this writing into this expression. From here on out, it's just stuff you learn in Chapter 5, and depending on the functions I choose here, this can be relatively easy Chapter 5 stuff or a little bit harder Chapter 5 stuff, but generally speaking, it won't be that bad. The hardest part is just setting up the integral, so make sure you understand this. To evaluate this integral, well, the pi is a constant, so I'll pull that out in front. So I got pi times the integral from 0 to pi over 4 of cosine squared x minus sine squared x, which I now have written here. And you're like, oh man, this is going to be miserable. Well, yeah, it is going to kind of be miserable. We got some trig powers going on here, and trig powers when the power was even was the ones that you don't really like. However, rather than having to do the problem twice, we could take advantage of the Pythagorean identity and maybe say that this cosine squared is 1 minus sine squared. So we could, if we wanted to, rewrite this like this, which might not seem like we've done anything good so far, but now we can put these sine squareds together, and that'll kind of cut down on the amount of times we have to use formulas to reduce these trigs. Evaluate this integral and we're done. The trick to evaluating this integral is remembering from 5.7 that sine squared x is equal to 1/2 times the cosine of 2x minus 1. Maybe this is a formula you remember way back from 5.7. So using this formula here, I can replace this sine squared x with 1/2 cosine 2x minus 1, but the 2 and the 1/2 will cancel each other out, and that will leave me with just cosine of 2x minus 1, and be a little bit careful with your parentheses here. Sine squared x is equal to all this stuff, both of the terms, so you need these parentheses to make sure you're subtracting this negative 1 as well. And now when I distribute this negative to get rid of the parentheses, this negative 1 turns into a positive 1, and this positive 1 and this positive 1 give me 2, minus the cosine of 2x. So I'm finally ready to take an antiderivative. I'll leave this pi out on the outside. The antiderivative of 2 would be 2x. And then the antiderivative of cosine of 2x, well, sine of 2x is almost the antiderivative of cosine of 2x, but if you took the derivative of sine of 2x, you'd get an extra 2 from the chain rule, so I need a 1/2 out in front. If you have a hard time with that logic, use substitution, u equals 2x. I think you'll get to this point right here. And then what I need to do is evaluate this expression from 0 to pi over 2. So my bounds of integration were supposed to go from 0 to pi over 4, not pi over 2. Somewhere up here I had switched a pi over 4 to a pi over 2 for no apparent reason, and then I just followed it down throughout the problem, caught it after the fact, so here I am after the fact going back and fixing things. So these all should have been pi over 4s, hence this will be a pi over 4, and now when we go to evaluate this thing, we change all the x's into pi over 4s. So 2 times pi over 4 is just pi over 2. And then from that we want to subtract 1/2 times the sine of twice pi over 4, so 1/2 the sine of pi over 2. And now we change all our x's into zeros, which I think works out pretty easily. 2 times 0 is 0. And then 1/2 the sine of twice 0 is 1/2 the sine of 0, but the sine of 0 is 0, so half of 0 is 0. Get all my parentheses closed up, and now maybe I can simplify this expression a little bit. Let's see, the sine of pi over 2 is just 1. So this is pi times pi over 2 minus 1/2, which I guess is a totally fine answer, or I would probably recognize I have a common denominator, so I can make it pi times pi minus 1 over 2, and then take it a step further and distribute the pi through the parentheses. So pi squared minus pi divided by 2 ends up being the volume of this region that we are looking for.